In this video, I'm covering exercises related to material covered in the chapter 17. As usual, you can see the question first, pause the video, answer the question on your own, and then see my answer. First question, which of the following pairs represents resonance structures? And you go by elimination. You eliminate those that are not resonance structures, and you're left with pair of resonance structures. A are not pair of resonance structures. That's two formulas of 1,3-cyclohexadiene, and they are rotated by 60 degrees. You cannot convert one into the other, let's say by means of curved arrows. If you number the carbon atoms and use curved arrows, you cannot arrive from one formula to one formula from another. So those are not pair of resonance structures. Second B, those are actually a pair of resonance structures, because if you use curved arrow and move a double bond, you go from one carbocation, one allylic carbocation to another. C, those are not pair of resonance structures because number of unpaired electrons is not the same. One double bond has been split into two unpaired electrons. So those are not resonance structures. Number of unpaired electrons in two resonance structures should be the same. And D is an example of isomerism called tautomerism. In a resonance, all of the nuclei remain in fixed positions. No nuclei moves. In this case, hydrogen has moved from one formula to the other, in addition to movement of electrons, movement of pi bond. So that's isomerism, known as tautomerism. So correct answer is B. In next question, which of the following compounds is not stabilized by resonance? So you identify all the compounds that are and then find one that is not. So first compound, compound A, has free electron pair on nitrogen next to a double bond. So obviously that's electron delocalization or resonance. That free electron pair and double bond, since they are next to each other, they are delocalized. In the next question, we have two pi bonds next to each other, two pi bonds separated by a single bond. So those are conjugated pi bonds, pi bond of a double bond and pi bond of a triple bond. So that's again electron delocalization or resonance. C, also a resonance, because now we have carbocation next to a double bond. So again, this is an example of resonance. Finally, in the last case, example D, we have CH2 carbon. So that's sp3 carbon that is intervening between free electron pair and a double bond. So in this case, resonance or electron delocalization is not possible, because free electron pair and double bond cannot delocalize. There is an sp3 carbon that is in the way. So correct answer is D. Question number 3. Which of the following compounds is stabilized by resonance? So opposite from the first one. So now only one will be stabilized. So if you look at first one, A, there is sp3 carbon between two double bonds, so there can be no resonance. In B, actually we have two double bonds next to each other, conjugated double bonds, so that's resonance. But we should check the rest to make sure that B is correct answer. So we have C, again sp3 carbon between free electron pair on oxygen and double bond, so again prevents electron delocalization. And D, the same thing. We have very similar compound, again an ether, and it's an allyl ether in both cases, C and D. And again we have sp3 carbon between free electron pair on oxygen and a double bond. So correct answer is B. And then question number 4. Which of the following carbocations is the most stable? So first carbocation is benzylic cation, and it's secondary benzylic. B is primary benzylic. So secondary is more stable than primary, so A is more stable than B. C is tertiary benzylic. That's even more stable than secondary, so that's more stable than A. Sorry, B is just ordinary primary carbocation, not primary benzylic. I made a mistake. That's very low stability. D is primary benzylic carbocation, but that one has stability lower than secondary or tertiary. So if you consider stabilities, C is the most stable as tertiary benzylic, then A, secondary benzylic, then D, primary benzylic, and finally B as ordinary primary carbocation would have the lowest stability. Since we are looking for the most stable, correct answer is C. Next question. What is the order of stability of the following free radicals from the least stable to the most stable? So when we consider these free radicals, we have stability of 1 is secondary benzylic, 2 is tertiary, then 3 primary allylic, and 4 tertiary benzylic. Benzylic are more stable than allylic with the same degree of substitution, and tertiary would be the least stable. So 2 would be the least stable, so A or C are correct answers. And then next in the order of stability is primary allylic, that's 3. And so that means A is correct answer. So least stable is tertiary free radical, then primary allylic, then secondary benzylic, that's 1, and finally tertiary benzylic, 4. Next question, which of the following alkenes would you expect to react the fastest with water in presence of sulfuric acid? That's one with electron donating groups, if any. Electron donating groups increase electron density on the double bond and make double bond better electron donor, better nucleophile. Conversely, electron withdrawing groups reduce reactivity. So when we consider 4 compounds, A is ethene, no substituents, default reactivity. B is compound that has 2 electron donating groups, 2 methyl groups. They're not very strongly electron donating, nonetheless they are electron donating. C has 2 electron withdrawing groups, fluorine and nitro group, and D 4 electron withdrawing groups. So all those have reduced reactivity. So correct answer is B. Question number 7. In the following example, identify the lowest and the highest energy resonance structures. So the lowest energy structure is going to be the one without any charge separation. And that would be structure 1. Now, structures 2 and 3 have same number of unpaired electrons, same charge separation, 1 positive, 1 negative. But structure 3 has what we call unnatural charges. In that structure, we have oxygen. Sorry, it's not unnatural charges. Sorry, I made a mistake. Structure 3 has carbon that is electron deficient, that has sextet, it does not have octet. So in this case, we are not looking for unnatural charges where one atom has electronegative atom has positive charge and electropositive atom negative charge. That would be another possibility for highest resonance structure. In this case, we are looking for atom that is electron deficient, does not have an octet. That would be an indication of very high energy resonance structure, and that's structure 3. Question number 8. Predict the major product of the following reaction. So it's a reaction of styrene with hydrogen chloride. Reaction proceeds regioselectively in such a way that only benzylic carbocation is formed. So hydrogen adds to terminal carbon, benzylic carbocation is formed, and that carbocation reacts with chloride anion with nucleophile to give the final product.